Let me try to share my slides. Okay, are you able to see them in full screen?
Yes, that looks fine.
All right, perfect. Yeah. Okay, so yeah, hello everybody. So yeah, today I would like to talk a bit about the primary vertex reconstruction for the LHCb upgrade. And as you already might know, to achieve real-time reconstruction of proton-proton collisions at 30 megahertz for the upgrades within the available resources, we developed two solutions. The first one being the so-called baseline solution on CPUs, and the second one, the so-called Allen project on GPUs. And for more details on both, I would just refer you to the dedicated talks at this conference. Now in this talk, we want to have a closer look at one part of the reconstruction sequence, which is the primary vertex reconstruction. Now, why do we need to reconstruct the PVs? So the PVs are the interaction points of the proton collisions, and we need to reconstruct them to discriminate between short and long-lived particles, and then to be able to trigger undisplaced signatures. How are we able to reconstruct them? We can reconstruct them using the vertex locator, which is the detector around the interaction region, where you can here see a scheme of the ReLo detector planes shown as blue lines, and the interaction region marked with a black circle. And in Run3, we have about 5 to 6 visible PVs per event, which are PVs leaving enough tracks in the value for us to be able to reconstruct them. And they are spread in Z along the beam axis with around 6 centimeters, and then the transverse plane in X and Y about 20 microns. The particles originating from the interaction region then traverse the value as straight lines, and based on those reconstructed straight lines in the value, we are able to reconstruct PVs. So what kind of performance do we need to reach, at least in Run3? So to give you an impression of that, here's the performance reached during Run2, where you can see the primary vertex reconstruction efficiency as function of the number of tracks of the Monte Carlo PV at different tunings. And now the challenge for Run3 is that we need to be faster at larger event multiplicities without sacrificing any physics performance. And for this, we needed a new algorithm. And of course, now we need implementations for CPU and GPU architectures. Now this new algorithm is based on the idea that looking only at the Z-axis along the beamline is sufficient for identifying PV candidates. And this is demonstrated here, where on the top you can see the spread of simulated PVs in X and in Z along the beamline, and compare it with the bottom, where you can see the spread in X and Z of a track around the PV. And you can clearly see that looking at X on the left, you have not any chance to discriminate between different PVs. But if you look at the spreads of a track around the Z position, you can see that it's much narrower than the distribution along the beamline. You might have a chance to identify different PVs. Now, with this algorithm, what we start from are, of course, the reconstructed tracks in the velo, where we have the track state at the first measurement, which is a measurement closest to the interaction region, and the covariance matrix from a simplified Kalman filter. Then what we also need for this algorithm is the beamline position, which we know from the closing procedure of the vertex locator. And we assume here that the beamline is parallel to the Z-axis at a certain X and Y coordinate. Then, as a first step, we extrapolate the Velo track states to the point of closest approach to the beamline and cache the invariant covariance matrix at this position. Here we can, for example, gain throughput by extrapolating the tracks in parallel, because the extrapolation is, of course, independent. And also, we never update the covariance matrix again when we use it later. As a next step, we fill a histogram with a density distribution around this set at the point of closed approach to the beamline of the tracks, where this density distribution is a Gaussian distribution which takes into account the uncertainty on this set value. And here you can see a typical histogram filled by the algorithm. And you can see clearly already by eye peaks which will then correspond to the PV candidates. And here, for example, we can gain speed ups by filling the histogram in parallel. So as I said, this density distribution takes into account the track covariance matrix, and this is kind of new for LHCb, explicitly taking this error into account. And this uncertainty is also dependent on the track slopes Tx and Ty in the x and y direction, according to this formula I put here. And then the contribution to a certain bin in the histogram is of course given by integrating this Gaussian density. And to make it faster, we approximate this integral by using templates or approximating Gaussian with polynomials. Then we look for peaks in this histogram, and here you can see marked with blue lines the peaks identified by the peak finding. And we get then the vertex candidates at the x and y of the beamline and the set positions of the peaks. Now, so far, the algorithm was implemented for CPU and GPU and following roughly the same logic. The next couple of steps will deviate slightly for reasons I will go into in a second. So focusing on the CPU, as a next step, we assign the tracks to each vertex candidate using those cluster edges marked in red, which are also graded by the peak finding. And then finally, then of course you could worry about the vertex track combinatorics when doing this association, but it turns out that this step is actually quite faster than the CPU, being due to that the vertex candidates are already sorted and set and using some fast partition algorithm. And then finally, the last step, we of course do a fit of the vertex candidates using a typical adaptive fitting algorithm, where each track corresponds or contributes to the fit with a weight, which depends on the chi-square of the track with respect to the primary vertex candidate, where the chi-square is a function of the residual in x and y of the track to the vertex candidate, as well as the track covariance matrix elements of x and y. And here you can see a typical weight distribution as function of chi-square, where the weight gets smaller at larger chi-square with a cutoff at a certain point. And here we can gain some throughput by vectorizing the sums of quantities derived from this sum over all the chi-square, which we need in the minimization. And now we can have a look at how this new algorithm compares with the previous implementations on the CPU. And for this, you can here is shown the primary vertex reconstruction efficiency as function of number of tracks in the PV and as function of the set position of the simulated PV, where the new algorithm is marked with red dots and the previous one with orange dots, and the underlying distribution shown in gray. And you can clearly see that the new algorithm meets or even exceeds the physics performance requirements and turned out to be about 6 times faster than the previous one, where we gained roughly a factor 2 from vectorization. Now, going back to the GPU. So in a sense, we combined the last two steps. So we thought that partitioning tracks to a certain vertex candidate might not be the right choice for GPUs because it might not necessarily be easy to efficiently parallelize. As an alternative approach, we do not assign tracks to a particular vertex seed, but let each track contribute to each vertex fit with an appropriate weight. And then this means we could fit each vertex independently, and within each fit could parallelize the loop over all tracks, which we thought might fit quite nicely on GPU architectures. So how could this weight look like? So we took a lot of inspiration from multi-vertex fitting approaches. where the weight now not only depends on the chi-square of the vertex CTO fitting, but also on the proximity of other vertex candidates close to your track. And so here you can now see this modified weight distribution as function of chi-square, where the blue line shows the weight without any competing vertex, and the orange and green lines if you have additional competing vertices with a particular chi-square. So this now means that a single track can contribute to different vertex fits. And of course, we need to keep it different vertex fits independent of each other. So the initial seed positions are used to define and calculate the chi-square of a track with respect to the other seeds. And now we compare the PV reconstruction efficiency of the CPU and GPU implementations, again, as a function of the number of tracks in the simulated PV and the set position of the simulated PV, where now the baseline CPU is plotted in red dots and the Allen GPU implementation is blue. And you can see for the most part, the efficiency looks fairly similar, only that in case of the GPU implementation, it's a bit lower for low multiplicity PVs and at the edges of the set distribution, which we explain by the input track states being a bit different between the two implementations, and also the fitting approach being different, as I just told you. And of course, this is something we want to improve and tune in the future. Now we can also compare the solution of the reconstructed primary vertices. So here is shown the resolution in X on the left and Z on the right. On the top, it's a function of tracks in the simulated PV. On the bottom again, as a function of the set position of the simulated PV. And you can see overall between baseline in red and Allen in blue, it's very similar. And yeah, finally, about the timing of this new algorithm. So in this case of the CPU, this algorithm actually takes now very little time, only about 3% of the first stage of the software level trigger, the LHCb, while for the GPU, it's a bit more, about 16%. Of course, you cannot directly compare these numbers because they are determined in different conditions. That this is just to give you a feeling of where we still could improve. So in case of the GPU, it seems like there's still room for optimizations. And yeah, to further break down the timing, here you can see where the time is spent on the GPU for the primary vertex fitting in different parts. And you can see that, of course, most of the time is spent in the fitting as expected, followed by the peak finding, whereas the histogramming extrapolation parts take a little time, which means that we should try to optimize the peak finding and fitting part a bit more and try to make it faster. And yeah, this brings me already to the end. So to summarize, a new algorithm for PV reconstruction was developed based on a histogramming approach along the beam axis, and it was implemented on CPU and GPU architectures. And this algorithm meets the throughput and physics performance requirements in both cases, so for the CPU and GPU, and was thus chosen as to be the nominal approach. And yeah, finally, just a small pointer to things happening in the future, machine learning approach described in the presentation by Marian Stahl, also in this conference. So yeah, that's it. So thanks for your attention.
Thank you, Florian. Please raise your hands for questions. We're quite well in time. I see none so far, so maybe I have one. What is the precision you get by simply peak finding? So if you don't perform a fit to get the best position, can you do something simply by finding the peak, and how precise would this be?
So I don't know exactly how precise it is in SAT. It's not too bad. I think, but I don't have any numbers on top of my head. The problem is, of course, that you have not the right X and Y position.
Yes, sure. I was just thinking because it's much faster than actually performing the fit test can be used for anything.
And of course, you don't get, just by looking at the peaks, you don't get the covariance matrix of the vertex, which you might need later in your set.
Indeed, yes. Any more questions? Okay, I don't see any. So then thanks again, Florian.
Yeah, thanks to you.
And I think we'll stay again with LHCb and another talk by Louis about the HOT1 sequence.
Yep. Can you hear me again?
I can still